You know what? No, we're going to use Jupyter. So what's up, guys? Welcome to my first stream. Today I'm going to try to use a decision tree to analyze some basketball stats data that I've downloaded from basketballreference.com. So I've already got the data for multiple years here. Maybe I'll make a video in the future about how to go through the basketball reference and scrape your own data. But for right now, we are going to deal with what we've got. So right now, let me actually just start a new notebook. Okay, so I just like using Pretty Print for making things better. What else? What's the scikit-learn import? So we're going to try to predict, using a decision tree, what position a player plays based on their statistics. I've worked with decision trees a little bit. I'm in a machine learning course right now, and we had an assignment about it that was actually due today. So I am going to work with the decision tree just because it's what I'm most familiar with at the current moment. Decision tree. Let's copy these imports. So forgive me if I do a lot of Googling during this. I'm no expert by any means. So man. CSV. We'll use the 2000 data, and we will call it NBA. Okay, wonderful. What is the read CSV? You know what? We're just going to copy that and paste it right here. And I said we were going to use 2000. Okay. So now we have our data in. We've got these categories. What is the right there? Oh, this will work too. Cool. So let's get a list of NBA. Okay. So let's drop the first two columns since we saw those and they look like this. They seem to be indexes from previous times that I've imported this. So PD, nope, NBA dot drop let's try this. UNNAMED colon 0.1. Does that work? Okay. It does not. So what if we did this? Dropping a column. Drop labels none. What about an example? df.drop columns. Seems like that's what I did. nba.drop axis equals 1. One of the axis is horizontal and one is vertical. I forget which is which. Columns. Maybe that's how you spell columns. Got it. Now we drop 0.1.1. Got it. Okay, so what's happening is every time we import it, it's creating a new index column, which is this column. It's using the old index column as it's creating a new column for that called unnamed 01. So what we're going to do to get rid of this is move it to the next block. So now we are going to remove unnamed 0.1 and unnamed 0.1.1. And then we should have, I forgot the colon. That's odd. I got it. NBA equals. So what we did is we just changed it, but we didn't save it back to the variable. So now we're saving it back to our NBA variable, and we are going to print it back out, and that is what it should look like. So, you don't spell columns with two L's. COLUMNS dot values. Is it? There it is. Okay, so these are our values. We are going to use these as our as our feature and our label data for our machine learning model. So I'm just gonna call this features. What a feature is it's a predictor. We're probably not going to use the player name because that's not really going to go into effect to predict what position they play. We're not going to use, what else? Age, because again, that's not going to have a lot to do with what position they play. But everything else will go into our machine learning model as a piece of data. It'll be something that it considers when it's trying to determine what position they play. We'll have a label, which is going to be our position. I'll just cut it out of here. And I will say label equals position. So now, looks like I messed up the formatting up here. So now if we put these into our data frame, so for example, NBA features is going to print out everything, but notice how we're missing the position column. That's what it's going to try to predict. But our position column up here in our original unnamed or unchanged data frame is in terms of abbreviations. It's not in terms of numbers. So we're going to need to change that before we can actually put it in. So to show you what the position label or the label data frame looks like, we'll do the same thing with the label. Spelled it wrong again. There we go. So now we just have a list of different labels. So this is what it's going to try to predict. So now we need to go ahead and change all of this into numbers. And how I'm going to do that is create a dictionary. Position dict. And forgive me if I mess up on this. I'm not exactly sure how to do it off the top of my head, so it may take some trial and error. I'm going to use PG, our point guard position, equals to 1. Our SG, shooting guard position, equal to 2, because these are common abbreviations in basketball terms. Our SF position, small forward, equal to 3. Our small forward, power forward, PF, equal to 4, and our C equal to 5. So now if we say the goal of what we're doing right now is to be able to just directly input this value into this dictionary and it will spit out a number. So that way we'll be able to recreate our position data frame using numbers instead of these abbreviations. So this would be a 2, a 3, 1, 2, 1, 2, 1, sorry. So let's see if we can figure out how to do this. NBA, let's try iLoc 0. That should give us our first player, and his position is that. So let's try NBA label iLoc. Okay, so this gives us our first player, which is Tariq Abdul-Wahad. It gives us his position as shooting guard. And what we are looking to do here is replace this value with this value. So let's try converting it to a string and printing it out. Okay, so we have our position shooting guard. Is there a dot value? Nope. Okay. Let's see if Google or DuckDuckGo gives us a nice answer for this. Trusty Stack Overflow. MP where? Doesn't look like exactly what I'm looking for. I'm sure it would work, but I don't want to spend too much time working on it, looking at it. this looks like something that may work a little faster. Replaced with other values dynamically. This differs with updating with loc or iloc, which require you to specify a location. Okay, so this looks simpler. How to find the values that will be replaced. Numeric string, okay, that's what we're looking for. Numeric values equal to replace will be replaced with value. Okay, so let's pull this up here, okay, and bring it over there, and this over here. Okay, so what it looks like is we need to NBA label dot replace. Let's try to pass in the position dictionary as our toReplace function. ToReplace equals, and our, what else? Dicts can be used to specify different replacement values. For example, replaces the value A with B. Okay, so that's what we're looking for. To use a dict in this way, the value parameter should be none. Okay, so let's try that and then use inplace equals true. Value equals none, and you know what, let's leave the inplace equals true off for right now until we're sure that we've got it right. Oh, we got it. Awesome. So that was quicker than I expected it to be. Let's create a y variable and set it equal to that. So now we should be able to print out our y variable, and it looks exactly like what we want. Okay, so now we need to apply the machine learning model, which is decision trees, as I said before, to this data. So now we have all of our NBA features. This is everything that we are going to try to predict with. So we need to look at it and see if there is data we don't need. So what we're looking for here is information along this row or a full column that we're not interested in having. So to me, I don't think player name will be all that valuable because it is a string, and it's not like you can use someone's name and determine what position they play in basketball. So we're going to eliminate that out of that. I don't really think age is going to have anything to do with it, but I'm going to leave it in here. And once we get the actual machine learning model built, we will remove it and see if it does better versus what it's doing now. So team, we don't really need that. And it's also a string, so we can't really process that at the moment. So games, we have that. It looks good. I feel like that might have something to do with it. It may play a small part. Game started, same thing. Maybe we'll try it without games and game started once we actually get going. Minutes played, field goals, field goal attempts. I think each of these will have something to do with the outcome, but we can play around with it once we get the model built, and we will see what it looks like. So I'm going to rerun this and rerun this. Now this is what our new data looks like. So now we need to try, just going to do that to shorten up the display, and I'll put it right there. Okay, so now we need to figure out how to apply the machine learning model. So let's look up sklearn decision tree. Okay, so looks like we are creating a decision tree classifier and we are using it to fit. So let's come over here and CLF, which I believe stands for classifier. We are going to put in a decision tree, ASSIFIER, decision tree classifier, which just creates the decision tree. It doesn't actually fill it out or put any values into it, so we just have a blank decision tree right now. So just to show that off, let's try to print this and see what it looks like. So it tells us about all the pieces of our decision tree, like how we can, what it looks like right now. These are each feature of our decision tree. So we're using the Gini criterion, which we'll talk about a little later. There's two different methods you can do it. You can use Gini or you can use entropy. And in my experience, entropy works better, but we'll try it with both and just see how it works. Impurity, that has something to do with Gini and just decision trees in general. I'll explain a little bit more after we get to the end of it. So we will use our decision tree classifier. We will declare our variables. We'll actually do that here, right above this block. My bad. Right here. So our x variable, we'll call it a capital X, equals NBA features, and our y seems to be our label. So we now have our x and our y set. So just to show, x is our features that we're going to use to try to predict, and y is what we are trying to predict, what position they play. So now that we have this set, I will put it up here. So delete that. Now we want to clf.fit, and we'll talk a little bit about what this method does in a little bit once we can actually see the decision tree. But this is the most important part of the actual machine learning model. Okay, why did it not work? Contains input infinity or a value too large. Okay, so apparently something in our data is not working. Let's try just importing that. All right, so we know that everything in our y, in our label, is good because we changed it all right here. And these were the only options. So let's just view it just to be sure. We are using 2000. So right here, okay, it looks like those power forward, small forward. Okay, it looks like there's only a few. So let's go through and handle them individually. We are going to position everyone up. So if they're playing 3 and 4, we're going to just put them as a 3. So let's go back over here and add in SF, PF, 3. What were our others? Let's put it over here. Maximize this. Oh, there's one. Power forward, small forward. So I think instead of what I just said, we will put the first one as their main position. So the last one was small forward, power forward. So this one's power forward, small forward. So we will just use this one as their main position, because I believe that is how it was intended. So PF-SF :3. Nope, :4. Now looking for another. Did I miss one? Small forward shooting guard. I missed that one. SF, SG. So 3. I believe I said there were only 3. Power forward, small forward. We got that one. Awesome. Okay. So let's run this again and see if we actually have it. So let's try that. Look at our Y. And it looks like it did before. We could view the whole thing, but I think it would just be easier to plug it into the model and see if it'll accept it. X and Y. Okay, so we're still having an issue. Too large for data type, float 64. Okay, so we're still having an issue somewhere. It could not be in this column, could be in another column. So let's go back through our columns and see if there's anything that could look funny. 2-point percentage. Let's open this in Excel. I think it would be a little easier to look at. $2,000. So let's try dragging it. Oh, that didn't work. Show file in browser. Ah. Show in file browser. Okay, wonderful. Well, I know where it's located either way. Desktop, stats, 2,000. There it is. Okay. So now we're in Excel, so we've got a better picture of everything. Are there blank columns? Okay. So we have our small forward shooting guard, which I believe we addressed. Small forward shooting guard, we did address that. Small forward, power forward. Check on the stream just to be sure it's doing okay. Awesome. Looks like I'm live now. I'm not seeing anything, you guys. Let's try this. Stats 2000. Open it with text edit. Now let's look for a comma. Okay, so it looks like our Jackson, power forward, Dallas. Bobby Jackson, nope. Jaren Jackson. Am I crazy? I'm in 2000. I'm looking for Randall Jackson. Randall Jackson. Randall Jackson, right there. Okay, so we are missing something in that column. So let's address that, okay? Field goal percentage, that's what we need to go through. The reason that we're struggling with this is because the model can't handle non-number values, and it's showing that as a none value, or as it's a numpy, N-A-N, or nan, or however you say it, value. So let's go through and try this. FG. This could be just a cheap way of doing this, but it worked before, so let's try it again. To 0. Let's change it to an actual 0. Okay, it doesn't look like we can put that in. That's because we don't have NumPy imported. NumPy is a Python numeric library. It helps us do some different mathematical operations that you can't just do in plain Python. So let's try this. All right. So now let's go ahead and try that. Okay, we're still having issues. Where did I put it? Open with, can I open this with Sublime? Yeah, there we go. That'll be easier to deal with. Okay, we're looking for double commas. We have Randall Jackson again. And we don't have another one. Okay. So that is our only null value. You know what I'm gonna do? I'm going to go in and change it right here. And then we're just going to import everything again. It was Randall. We want that to be a 0, since he didn't take any field goals and he didn't make any field goals. So technically his field goal percentage would be undefined, but we are going to make it 0 because that's more accurate for the data, in my opinion. Save as 2000 index-1.csv. Okay. So we now have, clean up by name, 2000-1.csv. 2000-1.csv. And real quick while we're here, I want to make the actual index column, I want to make, instead of it creating a new index column, I want it to use our current index column. So let's figure out how to do that. Let's check out the pandas documentation. Our header index column. Okay, so it looks like we have index column in right now, but it's not doing something for some reason. So we're going to try to use the header argument instead. So see, we have index column right here. Let's try header equals 0, which should, I think, make it use the top number, or the top, as our index, or as our header value. So it will make it use these, which it was already doing. I don't know why I did that. And we want data type converters, true values, false values. That'll be helpful. Skip blank lines, because when I was pulling all this information down, it was having trouble with that. Okay, so what if we look at index column? Well, how did I miss that the first time? Okay, index column. I think I told you earlier that this was the, what is happening? It's not to use the first column. Okay, so this, I don't know why I took it out. I was thinking it did something else. Index column should be 0. So let's try importing that and see what it looks like. Okay, let's try it one more time. And it looks like it's pulling things in correctly, but now we want to get rid of these like we did before. So let's uncomment this, select it all, and move it up here. And I believe we can dot to CSV. I forget what the method is called. It is to CSV. So perfect. And we will use that to just save it in after we've deleted these columns. To CSV 2000.csv. Okay, so what this is supposed to do is change our 2000 CSV, which is right here, and take these two columns away. So it will just have one index column. So let's look and see what it did. And it looks like it worked. So no need to run this one again. We have that, which is the same. that, which is the same, I believe. Let's check Randall again. Randall has a 0 where it's supposed to be. He has a 0 in most columns. He didn't play a lot. He played 1 minute. That's a good career. I bet he got paid a lot for it. Okay, so now let's import 2000 again. And it looks like, since we've already deleted these columns, we don't need them again. NBA. Okay, so that obviously didn't work like I wanted it to. So let's print it like this. Okay, so we're still exactly like we want it. And we have our column values, which are the same. So we're still using the same features, the same label, and the same position dictionary to convert. And we have our field goal percentage dictionary right here, where we changed Randall from a nan value from NumPy to a 0. Now we're setting our features to X and our label to the numeric values, and then we're showing it again. So we've still got everything that we need. So I'm going to delete this just to make it cleaner. And here, this should work, fingers crossed. Perfect. Okay. So now we have a classifier that is now fitted. So looks like it didn't save, so let's CLF equals that. I don't know why it's not saving. Let's look back at our documentation, which I put over here from scikit-learn. Okay, decision tree classifier, CLF fit, and then test trains. So there's also a method called test train split, something like that. Let's look at it. Scikit-learn. Train test split. Okay, so how does it use it? How have I used it is the real question. Decision tree. Right here. So in the past, when playing around with this, I used it like this. I put in X, Y, and here this isn't the same thing. I was trying to predict age, and I obviously didn't do so well, which is why we're trying to predict something else right now. So let's try copying this and bringing it back over to our program. And let's, dang it. Okay. And I believe we used a capital Y here. So what this is doing is it's splitting our data into pieces. It's giving us some data to train with and some data to test with. And it's a convenient model, it's a convenient method because it's taking our existing full set of data and it's splitting it 70-30 into 30% test data and 70% training data. This random state, let's figure out what this random state is. Random state controls the shuffling applied to the data before applying the split. Pass an int for reproducible output across multiple function calls. Okay, so it's just randomizing things in a predictable way. So we could use 2, and then we could use 2 again the next time, and it would turn out the same. So instead of using 1, let's use 6, for example. And that should give us 4 variables. So it will spit out these 4 variables. And now let's try to put in X train and Y train. Okay, so now CLF. Okay, so we're still getting nothing for our CLF. Okay, so back to our decision trees. And then we want tree.plotTree, so that should show our decision tree in matplotlib. Figure, we'll just call it fig equals this whole line we just imported it directly. We don't need the tree. Okay. Fig. Matplotlib. Huh. Looks like I've looked at something helpful before. Tree.plotTree, and we are using matplotlib. So let's try these. We'll put it here and take this away. NBA.png. Okay. Our class names, our feature names is what we have up here as features. So we are going to plug that in just so it knows, and then we want our class names as label. Filled is true. That creates some color here. And then we want is saved. So let's run this again with that tree. Everybody imports it like that. List index is out of range. Okay. Did that work? Same problem. Class. You know what? Let's try that. List. Well, we got something. We just need to be able to see it. Okay, so we will deal with this in a second. For right now, we have a working tree, which is what our entire goal is, but we don't know how good it is. So let's figure out how to test how good it is. And for that, we're going to use this metrics package from scikit-learn. And what that's going to do is take our test data and plug it into our model that we've created and trained right here. And it's going to give us a percentage of how well we did. And I already have this method written over in the decision tree that I made here. And let's paste this in and see what it does. So right here we are getting Y predictions, which is the classifier.predict, and we're using xtest, which we get from right here. So we're testing it and we're seeing how it did. So let's just run this and see what it did. Okay, so it looks like we got decent accuracy based on stats. Just using the Gini decision tree classifier. And all this does is it prints out the accuracy of the model using the y-test and y-predict, our predictions versus our y-test. So these are our labels of y-test. These show, this is our randomized sample of the different players and what positions they play. Our Y predictions is the predictions that we got from right here of what positions that those players say. So ideally, in a 100% accurate situation, you can guess that you can say that Y prediction should equal Y test, because Y test is the correct answers and Y predictions is their guesses. And we're testing how well they did, which is 43%, which in my opinion is not that bad. Especially considering I was getting 3 and 6% accuracy when trying to predict age. So 43%, I'm happy with that. So let's try the entropy tree. What is it? Scikit-learn decision trees right here. I want the random state 0, iris. Everybody uses the iris data set. Lame. Make your own data set. It's way more fun. Okay. So now we're looking for this, the decision tree classifier. Let's just search the scikit-learn documentation for it. And there it is. So we're looking for criterion. And we can use the Gini, which is the default, or the entropy. And we're going to try the entropy just to see if we get a different result. So criterion, back to Jupyter Lab. We're trying criterion equals entropy. And we're going to run the exact same everything again. So we should get an accuracy result as we got right here. So let's give it a shot. So we got 44% accuracy. Not great, not terrible. I'm actually really happy with that. So let's now work on trying to view the tree for each of these. So we're going to want a block right here with this data that I just deleted, and one right here. So let's look at the difference in what the trees look like. Okay, so we've got nothing right there. Figure. Oh. Pretty similar, actually. Huh. Okay, so in the decision tree module, I found this somewhere online and I don't want to waste your time, so we are going to copy it on over and I will talk about it. That's not right. Right there. Okay, so now we've got it put in, and we are going to run it. Feature columns. I think we just called that features.
We did.
Our label is all. Okay, let's see if that works. We don't want it called tree.eps. We want it as, that'll work. Let's look at it. Where is it? Open a new browser tab. Let's open the file. Okay, so we have a tree now that actually helps us decide what position these people play. So from right here, we're looking at, okay, if their 3-point average or 3-point attempts is over 0.35 a game, then we go to the true side, and if it's less, then we go to the false side. And this calculates entropy, and we have 307 samples where this is true. So let's go over this way. Blocks, it now asks about blocks, and if there's more than 0.15 per game, then it's going to go to the true side again, which I'm going to again assume is the right side. Assists less than 5.55, which is a lot. 88 samples, so 88 players had this be true for them. So now we go down, and looks like it's cut off right there. But you get the point. It's going to come up with a bunch of questions to ask and go down and try to use those questions to predict these positions. All right, so let's apply this to the first one as well. So we want this as entropy NBA tree, and we are going to run that, and then copy this, paste it here, and we got features, and we want this named Jenny NBA tree.eps. So now we are saving this, and see we have our entropy tree right here, and now we have both of our trees, and they're very similar. It looks like in my previous examples that I've worked on, they have not been similar. Now I think would be a good time to go into why they are different. Entropy itself is entropy is a calculation of how many questions you need to ask to arrive at a correct question. So I think it's best identified with an example. I'm going to pull up the YouTube video that really taught it to me. Oh wow. StatQuest, information gain, decision trees. And this right here was the video.
Hi, I'm Luis Serrano, and this is Shannon Entropy and Information.
Let's not listen to him. Where is it? It's right here near the end. So if you have this, then if you have this set of things in a bag and you're going to pull them out, you have a 1/4 chance of pulling each one of them out. So to answer what it's going to be with certainty, you need to ask at least 2 questions. Is it A or B? And if it's yes, then it goes left, and if it's not, it goes right. And your percentage of that is 50%, because half of your balls, or half of your letters are A and B, and then half of them are C and D. So half are going to go this way and half are going to go this way. And since it's evenly divided, half of those are going to go this way and half of them are going to go this way. So you take your times 2, which is how many you have. So you have 2 A's, and you multiply your percentage. So you have a 1/4 percentage, or a 0.25 chance of getting one of the 2 blue balls. So you do this for every individual entry. and you will get entropy of 2. And that will tell you when you minimize the entropy, you lower the amount of questions you have to ask. So you will end up with less entropy for less question models. So if there was a better way to ask this, then you could calculate the entropy for each question, and you would end up with many less questions, and the least questions would have the least entropy. This is very, I guess, complex mathematically. As you can see, there's a 21-minute video that it took me up until this point to even begin to understand. But there's also the other way, which is the Gini impurity. And what impurity is it calculates how many it gets right. So if we funnel all of our answers down through, let me try to open this. Well, that's not helpful. Okay, we will go to stats and Gini tree MBA. Okay, so this can't be right. There we go. That should be right when it generates. That's why they looked so similar, because we were dealing with the same photo. Okay, now we have different ones. So we are seeing our Gini impurity, which is our Gini is 0.0. Gini shows you how many answers you got correct versus how many answers you got wrong on a specific node. Each of these are called leaves, or nodes, and then at the end these are leaf nodes. So these are just regular nodes if they have lines going to them and lines going away from them. And then these, so the ones at the ends, are leaf nodes. This is the root node. It's the one with nothing pointing to it. So right here, the Gini impurity is 0.518. And it has 78 samples. So approximately 51% of these were correct, meaning that it took 51 of them, or it took 78 of them in, and it got 51 of them right. So this turns out to be the lowest Gini impurity of all possible nodes. And it's the function of doing Gini impurity like this is it wants to minimize the amount that it gets wrong for each node. So it tries to split it on every individual question that it could ask. So it asks about assists, it asks about free throws, it asks about defensive rebounds. And it says, okay, which of these is the least wrong if we divide the data like this? And it gets to three-point attempts, and apparently 0.35 was the best divisor. So it categorized things best by using 3-point attempts at 0.35. And then it says, okay, what's the next question that we could ask? And it determined that it was blocks and blocks, it looks like. So our blocks have a high Gini impurity, and that will go through, and again, it will perform the same process recursively throughout all of these nodes, which obviously there are many of, until it gets to something where the Gini impurity of just throwing it all into a leaf node and saying, okay, this is the answer, is higher than not having another node. So if right here it did decide, if right here it goes into one node that breaks down again, and it goes into one node that just stays where it is. So it decided on this node that it was better off not answering a question and just saying, okay, this is the answer. And here it decided that it was better off asking, okay, is their age above 35.5, or are their total rebounds less than 2.4? and it decided that this was a better question to ask than ask no question here, based on Gini impurity. There's a lot of Gini impurity videos online that can explain that concept a lot better than I just did. I would advise StatQuest. They do a really good job with machine learning and just the concepts of all of this behind machine learning and statistics and all of this. And I'm not a statistics person. I do have a math degree, but I'm not statistics oriented. So all this is just as new to me as it is to everyone else. And this guy really helped me understand it. Okay, so now we have predicted position based on all this information. So like I said at the beginning, let's try and cut out some of these and see if it'll do better, see if it'll do worse, what exactly will happen. So let's cut out age and see if that helps it or hurts it. So let's run that again, run that. Oh, it got better. And let's see what it pulls out here. So I think we went from around 42 to 46. I forget what it was here, but it's at 44. So it looks like Gini did better here than entropy, whereas entropy did better than Gini in the previous one. Okay, so let's throw that. All right, so let's put that back in, and is it capital or no? No, it is not. AGE. And let's take out games and games started. See how it does now. 47% accuracy and 50% accuracy. So it's an exact 50% right here. So it looks like without games and games started, this is actually a pretty good predictor. It can get it right half the time, which is more than I could do based on just stats. You know, I would guess power forward for small forward or whatever. So let's try this on an actual different year. So let's try 2012. And we're gonna have the same values since Basketball Reference is pretty uniform. And all this is the every stat for every player in the league. You can go to basketballreference.com and where is it? Seasons, award winners, league averages, NBA. Oh, this is pretty good data. Be an easier way for me to find it, like this. Data cleaning. This is where I was going through and trying to clean the data a little bit. I know where I pulled it from. This is the scraper that I used, so I'll probably use this, show this in a little bit, but here is the URL. Copy that, close PyCharm, and give this a shot. And we want HTML, right there is where we will put our year. So you can go to this URL and it gives every person's that was in the NBA that year. It's obviously a long list. There are 478 entries, but some are duplicates. For example, Sam Young played for Philadelphia and Memphis. Nick Young played for the Clippers and Washington and Toronto. So all I did for this was drop the duplicate entries. In the future, I'm going to go in and figure out how to add them all together and get a comprehensive stat chart for each player and kind of disregard the team stat. Not that that couldn't be useful, but you can't really do it if they play for 3 or 4 teams like Nick Young did or all these other people. So here's where I got all this data, and I'll share the scraping in the future. I'll actually put it on GitHub and post a link of it in the comments. But I got all this information, and I forget where I was going with this. Let's use 2012. Oh, this is the wrong one. We need here. Oh, I hope I didn't just run that and save it over 2000. I think I did though. 2012. Okay. And we have our same problem that we had before here. So I'm gonna just uncomment this line of code and save it. And now we've got rid of those extra 2 columns. Our column values should be the same. Features are the same. Xtrain, Xtest. Okay, so we're having our label issue again. So let's go in and take a look at it like we did before. Excel 2012. Blank. I'm not seeing anything. Okay, unknown label. We know that our error is coming from right here, but we don't know where exactly. So let's check X. And Y. Alright, let's open it up in Sublime. We're looking for the double commas, which shows that there is an empty column, which is the non-value which we were having before. It doesn't look like there is one, so I wonder what the problem is. Let's check it out on Stack Overflow. Unknown label type, unknown. What do you mean need unknown label type? So let's try. I know what it is. We're having the same issue we were having with the positions before. We have a dual position player that we didn't account for. Center power forward. Small forward, power forward, I think we accounted for that one. Small forward, power forward. Okay, so let's just add a center power forward in here, and we will call him a 5 because center is the position that comes first. Let's try it one more time. Okay, looks like it worked this time, and we got 54% accuracy in 2012, which, fingers crossed, that I think that's pretty good. Let's try it with the entropy. Gotta wait on this graph to generate. 55% accuracy in 2012. I'm actually really happy with that. So I think I'm gonna call it quits. We've accomplished what we set out to accomplish. I set up the machine learning model for a decision tree and ran through different years of the NBA, trying to predict player position based on player stats, and we got it right half the time, which I think is pretty good. So it's been fun, and I'll see you guys in a couple weeks.